Now, what have we actually proven here? Well, what we said was, some functions contain infinite loops, some functions do not contain infinite loops. And what we've shown is that it's not always possible to say which one it is and to then prove it. Can I give you an example of this kind of thing? Well, obviously not. Why not? Because an example would be of the form, for example, f of x doesn't hold, and you can't prove it. Well, I can of course assert that f of x doesn't hold for a particular f and a particular x, and also assert that you cannot prove it, but in order for you to be convinced, I would have to prove this, and I would have to prove this. And I just said that you cannot prove this. This means that I cannot provide an example like that. All I can say is that under this informal notion of proof, those kinds of functions and those kinds of inputs are out there. I just cannot tell you where they are exactly. Now, when we're talking about proofs in general, the kinds of proofs that you do, for example, in calculus, you would have to pinpoint exactly what you mean by a proof. And generally, what you mean is not the kind of thing necessarily that's implied by this. What you mean is by a proof is that you start with a set of axioms, a set of assumptions, and then from those assumptions, you derive theorems. So Kurt Godel's actual result, that has to do not necessarily with functions, but more with integers, is that with any set of axioms, you cannot derive all that you would want to derive about the integers from those axioms. So in order to give examples about integers, of actual proofs about integers, actual statements about integers that cannot be proven, well, you have to go into different sets of axioms and figure out what's going on there.